Okay, guys, stop. Quite a few things I want to go over today. All these homework assignments will be due next Monday. I'm making some slight adjustments to your homework assignment. So under 6.2, you guys can cross off 33 to 38 all, and then on the 13th, you can cross off 71 to 74 all. Okay, if you guys can turn to page 7 in your packet. Does everyone have the new unit packet, Unit 6? Page 7.
Do you have a October calendar?
Yes. Let me get that to you. Okay, so we're moving into this idea of antiderivatives, which is kind of going back from kind of going backwards with the derivative process. And I just want to show you real quick here the connection between derivatives and, why is slope and area? Why are they inverse processes of each other? So I want to show you real quick here. Let's say I had, we know what slope is, right? Slope is just y2 minus y1 over x2 minus x1, right? And we know slope is basically just a fancy, or derivative is just a fancy word for slope, right? Rate of change. Anything derivative is rate of change related. Now, what is the inverse? This is division, right? What's the inverse procedure of division? Multiplication. So let's turn this into a multiplication expression, right? x2 minus x1 times y2 minus y1. If you think about what that really means, x2 minus x1 is just some horizontal distance. Okay? y2 minus y1 is just some vertical distance. And what happens when I multiply horizontal and vertical component together? What do I get? I get area, right? I get area of a rectangle. So if I want to undo the slope process, I can go through this area or this area procedure. So that's why when we talk about antiderivatives and we talk about how we want to undo the process of derivatives, this is what's going to end up happening. It's going to be this area calculation that we're doing. So that's why everything with antiderivatives kind of has that area feel to it, because we're undoing the process of division and slope. Okay, so we're not going to get to the calculus portion until maybe tomorrow or Monday. So we're going to focus on the idea of approximating area using rectangles. Okay. So the graph of the function g of x is shown to the right. Approximate the area of the curve with n subintervals by using left-handed rectangles. So let's say we want to do 4 subintervals. Okay, so we're going to do let n be equal to 4. Now we know area of a rectangle is width times height, and there's a formula for especially if I want to subdivide this interval using, or subdivide this region using these numbers of intervals. The width is b minus a over n. It's my left and right, subtracting the left and right endpoints and dividing by n. So in this case, my a and b are 2 and 6. So I'll do 6 minus 2 divided by 4. 4 over 4 equals 1. So I want each subinterval. If I want 4 equal subintervals in this region, then every subinterval is going to have a width of 1. We're going to do left rectangular method. So what we're going to do is from 2 to 6, going to help us see that we have these 4 subintervals here. First subinterval, second, third, and fourth subinterval. And we're only looking at the graph between the, or we're looking at this region between the graph and the x-axis. And for each left subinterval, we're going to attach to the curve. So between 2 and 3, I'm going to choose 2 because 2 is the left endpoint of that subinterval. I'm going to attach it to the curve. Now, once you hit that point on the curve, you're going to draw a horizontal line over, because that's going to represent the height of your first subinterval or rectangle. Now, my second subinterval is between 3 and 4. I want to choose the left endpoint because it's left rectangular approximation. So from the x-axis at 3, I'm going to extend to where I touch the graph. Then I'm going to draw a horizontal line over to indicate that's the height that I want to establish for my second rectangle. Third rectangle, I'm going to choose f of 4. So f of 4, wherever that graph touches the x, wherever the graph touches the line is where my height of my rectangle is going to be. And then between 5 and 6, I'm going to attach a vertical line at 5 to the graph and let that hang over. So this is called a Riemann sums using rectangles to approximate the area under the curve. Now, obviously, this is not exact, right? We see that there's gaps here. So, but it should be a decent approximation. Obviously, we can improve our approximation by adding more rectangles, right? More subdivisions would cover more gaps, and the less gaps there are, the more accurate our approximation.
Wait, so if you have like if n equals infinity, can you actually get the exact? Or...
Yes, yeah. So we're going to talk about that, where if we can take the number of rectangles and let it approach infinity, then the idea is that we can get the exact area under the curve. So we have this limit definition of derivative that we learned, and there's also limit definition of area, which is the long way of doing things. But then we're going to talk about the more efficient way next week. Okay, so below is the graph of 4x minus 1/2 x squared. Use Riemann sums to approximate the to find the approximation of the area under the curve. We're going to do left Riemann sum, which is the same thing as left rectangular approximation method. And then we'll do a right Riemann sums. And we'll do midpoint and we'll do a trapezoid. So you can see all the variations. Okay, so first, I'm going to use this width formula to find the width. I want every subinterval to be the same width. So there's my A, there's my B, there's my N. So I'm going to start off with B minus A over N. So 6 over 3 is 2. So I want each subinterval to have a width of 2. I'm going to start at 2 and go to 8. So there's my first subinterval, my second, and my third subinterval. Each subinterval, I want to use the left endpoint to attach to the curve. And then sketch your height across. And we'll do it for each of our three intervals.
You let go.
That's right. Sometimes it can be over the curve, sometimes it can be below the curve, but we are focused on the fact that we want to attach left endpoint regardless of whether it's above or below. So here is an area approximation using these rectangles. Every rectangle has a width of 2, so I'll say 2 times f of 2, and f of 2 will represent the height of my first rectangle. So I want us to practice writing it out in function notation first. Okay. Does everybody see how I'm building my rectangles here? Width times height, and width times height. So f of 2, I think we can tell by looking at the graph, these are nice whole numbers here, but we can also plug into the actual function and get the y value. But here, let's just use the graph. What's f of 2 equal to? What's the height? 6. Okay. What's f of 4? 8. And then what's f of 6? Back to 6. Okay. So we just replace all of our function notation y values with actual y values, and then we can add up the area of our region. Okay. And once you do that, then do the same thing for right Riemann sums.
Right, Riemann, so you start from the right.
That's right. So for right Riemann sums, for each subinterval, you're going to take the right endpoint of each subinterval, attach that vertical line to the graph, and that is going to be the height of that subinterval. Now, what's strange about that third rectangle? Yeah, it's f of 8, right? F of 8 is 0, so that third rectangle is just going to be 0. So really, it's 3 subintervals, but really we're just adding 2 rectangles because of the fact that that third subinterval endpoint ends up being right at 0.
How do you know which one's like a better approximation?
We don't have to worry about that. Well, actually, we just slightly. We don't have to worry about, oh, you know, this is more better than between left and right. We're not going to be able to tell that much. But the below midpoint and trapezoid, we're going to tell that midpoint is going to be better than left and right, and trapezoid is the best out of all of them, assuming that you're using the same subintervals. Obviously, you can improve left and right by adding more subintervals, but we don't have to worry about, oh, left is, you know, this accurate and right is this accurate. Just kind of have a general idea that trapezoid is best, midpoint is second best, and then left and right about equal. Okay, everybody good with left and right Riemann sums? Now midpoint, let me show you the process for midpoint. Same subinterval, right? So from 2 to 4, from 4 to 6, and from 6 to 8. Now we're going to use the midpoint of the subinterval which is what? Between 2 and 4, we're going to choose
3.
3. So you're going to use 3, draw a vertical line starting with 3, go to the graph, and let that be the height of your first rectangle.
You're on free.
Oh, sorry. Thank you. You have to give a 6 back in. You do. Between 4 and 6, what's our midpoint? 5. So you're going to start at 5, attach, draw a vertical line until you hit the graph, and then you can let that be the height. Seven is the midpoint between 6 and 8. Attach that point to the graph, and that's your y value. So let's put in function notation first. First rectangle is width of 2, height is f of 3. Second rectangle, f of 5, f of 7, and then we can use the function, but let's just do approximation using the graph. All right, got to put these values in. The calculations here. I think 7.5, 7.5, and 3.5. Okay, lastly, trapezoids. Same subinterval, same A and B value, same 3 subintervals. So we're going to go from 2 to 4, 4 to 6, and then from 6 to 8. Now with trapezoids, you're going to attach both your endpoints to the curve, and then you're just going to connect the straight line between your endpoints. So you can tell that trapezoid just has a natural ability to reduce the amount of gaps between the curve and the x-axis. So you can already tell just by looking at the trapezoid shape that it's just going to fit the graph a little better. And this third shape ends up just being a what? Triangle, yeah. Now we don't have to adapt to a different formula. The trapezoid formula will just turn itself into a triangle formula. So here's the trapezoid area formula. It's 1/2 of the width times height 1 plus height 2. A way that someone described trapezoid is it's basically like a rectangle. There's a width component, And then the height component, you see how there's two different heights. So it's really just the average of the two heights, turning it into a rectangle, and then just width times height. So you can think of it as width times height, but then there are two heights, so I have to find the average of the two heights times the width, because of two different heights, and I can force it into a rectangle formula by finding the average of the two heights. But I write it this way, but it's just, if you can think of it that way, then maybe that will help you remember the formula a little bit easier. If you just think, oh, there's two different heights, I have to adapt it into a height formula for a rectangle, so width times height, but the average of the two heights. And height 1 and height 2 are just the heights of the endpoints.
How do I know from interval 6 to 8 that it's a triangle? Because it's like a curve, so it's not a straight line. Without,
Well, we're doing approximations using trapezoids, right? Now it's a triangle, but a triangle will turn itself, this will turn itself into a triangle formula because one was 0, one of the heights was 0.
I didn't see that you put a line there.
Oh, okay, okay. Yeah, that's right. It's a line. It's a geometric shape. Okay, so here is what the result will look like. 1/2 of the width times f of 2 plus f of 4, and then f of 4 plus f of 6, then f of 6 plus f of 8. I didn't spell out each of those y values, but it ends up totaling 34. Now, on the AP exam, and even on tests, it's rare that you're going to have to do Riemann sums with a graph. Typically, Riemann sums on tests as well as AP exams, it shows up more like table of values. So let me show you how to do Riemann sums with table of values. So let's go to next page, page 8. Okay, it says the rate at which water is being pumped into a tank is given by the continuous function r of t. A table of values selected of rt for a time interval from 0 to 12 minutes is given below. Use the following Riemann sums to estimate the number of gallons of water pumped into the tank during 12 minutes. Now, we know that Riemann sums is related to area. And when you have area, you know that your units are going to change. So anytime we're talking about area, we're gonna have to, our units will not stay the same, right? It's always going to be these two units multiplied together. So what's gallons per minute times minute going to give us?
Gallons.
Just gallons, right? So I want to help continually remind us. Anytime we're doing table of values, Riemann sums, you have to be able to change the units and think in terms of the adjusted units. So this is going to end up giving us information about the total amount of water that's pumped, not a rate, right? We start with the rate, but once we involve area, Riemann sums, our units are changing. So we're going to do right Riemann sums with 4 subintervals, okay, over the course of the 12 minutes. So the way that I want us to draw our, now we're not gonna graph these points. We're just going to use these rectangular intervals to help us, or these bracket intervals to help us see how to find it. So when you draw these intervals, you kind of space it out here. You can't tell that this is one interval, second interval, third interval, fourth interval. Now, when you draw your bracket intervals, don't start at the line. Start in the middle of your order pair. So this is one interval. And then when you go to the next interval, you're going to repeat the same point. You're going to pick up where you left off. You're not going to jump to the next order pair. You're going to start at 3 and go to 6. And then from 6, you'll go to 9. And then from 9, you'll go to 12. Okay, I see. Now, if you're unable to draw this correctly, it's going to throw off your whole interval. So just make sure that you're getting used to drawing these brackets correctly from middle to middle, and then you always are going to overlap with the next interval. Now, we're going to find width and height component and just add them up. Okay, it's not difficult, but I see a lot of students learn it incorrectly, and then it just throws off their entire work. It's kind of like a cascading effect. So you always want to subtract. Okay, don't add, subtract. So 3 minus 0, that's a width of what? 3. Okay, 6 minus 3, 3. 9 minus 6, 3. 12 minus 3. Now, for the most part, you're not going to have equal uniform width. AP exams, they love to give widths that are different, but in this case, they're the same. Okay. So my first subinterval, my width is 3, and the height, I want to choose the height that is coming from the R of t. So these are my y values. So the height of my first rectangle is going to be 13. So 3 times 13. That is the area of my first rectangle. Okay. Second rectangle, width is 3 and a height of what? 18. I want to choose the right endpoint. 13 is the left endpoint, left height of my second interval, but 18 is the height of my right endpoint.
Just multiplied by the right.
What's my third rectangle going to be? It's going to consist of what? 3 times 23. And my last rectangle? 3 times 27. Again, it's not difficult, but if you misread, sometimes I see students, they subtract the y values, and right. So we got to make sure that that we have this process down. Okay, so all this adds up to be 243 gallons. Is the approximation greater or less than the true value? So what he knows about these y values, these y values are increasing, right? So I'm just going to draw an increasing graph, and my right Riemann sums, basically every subinterval, I'm attaching the right endpoint. You can kind of see it, right? This is a over approximation. Over approximation. And the reasoning is because we have a right Riemann sum on an increasing function. That's all we need to say. Okay, you guys want to try the left Riemann sum with 4 subintervals? See if you can identify the width, identify the heights, and then multiply your area, add up your areas together. Is the approximation greater or less than the true value? Again, we have an increasing graph. If I attach to the left endpoint of each subinterval, my rectangle is all going to sit below the graph. And so my rectangle is going to be under approximating the actual area under the curve, under the graph.
There was decreasing, everything would just split, right?
That's right. Everything would flip. But there's no need to memorize it. I would just always sketch the graph and just convince myself visually. Yeah. Don't feel like you have to memorize these properties. Okay, let's talk about midpoint sum. I think that name midpoint sometimes can be misinterpreted. I know that's what they use, but I would rather think of it as middle or between. It's not, it doesn't have to be the exact midpoint, it just have to be between. So here it says midpoint Riemann sum with two subintervals. We're still spanning across from 0 to 12, but we're going to, let's see, we can go from 0 to 6 being one subinterval, and then from 6 to 12. Now, if you're given a table of values and they're asking about midpoint Riemann sums or midpoint approximation, they always have to give you an odd number of order pairs. They can't give you two order pairs because they're never going to ask you to actually find the midpoint between the two y values. You're just going to pick out what's in between. So just keep that in mind, that if they're asking you, if they're doing Riemann sums with midpoint approximation and a table of values, every subinterval has to have an odd number so you can actually find the middle y value. So what's the width of my first subinterval? 6, right? 6 minus 0. What's the width of my second subinterval?
6.
Also 6. Now it happens to be that 3 is between, exactly midpoint between 0 and 6, but it doesn't have to be. It could be a 4, it could be a 5, it could be even a 1. Okay, but all we're going to do is we're just going to pick out the y value that we see sitting here. No need for any calculations. Don't do add and add averaging the numbers. You're just going to physically find whatever that number is. That's your height. So my first rectangle is width of 6, height of 13. What do you think my second rectangle will be? 6 times
23.
23. Yeah. And that's it. Now moving on to trapezoids. Trapezoid sum with 4 subintervals. So we're going to go back to the 4 subintervals that we've did for left and right Riemann sum, right? Every width is 3. And every trapezoid only has 2 heights associated with it. Right? Sometimes I see students where a trapezoid subinterval spans across more than 2 order pairs and they want to add up all the heights. Only 2 heights associated with each trapezoid. So my first trapezoid is width of 3, height of 7 and 13. Second trapezoid, width of 3, height of 13 and 18. So this is how I would write it out. Technically, you could factor the 1/2 and 3 out, but more times than not, your subintervals will be different. So I just like to get in the habit of, let's just treat every trapezoid as its own thing. Let's not try to combine anything. It's just cleaner this way. Okay, we're not going to worry about the bottom of the page. Those are just more examples. I'd like to move on to page 9 and 10 and move towards this idea of what if we were to increase the number of subintervals to infinity, then technically we should be able to arrive at the actual area under the graph, between the graph and the x-axis.
That doesn't make sense. You can get infinitely closer to something without actually getting to it.
Right.
But
It's like a leap of faith. You just have to accept it.
okay.
I can't prove it. Okay, next page. So let me just review a few things with summation notations before we move on to this idea of, what would it look like if we were to increase the number of subintervals to infinity. So sigma notation here. Basically, sigma notation just allows us to represent in contains an expression that we want to add up a bunch of terms together. So my index is the variable that is going to change within my rule of expression or my argument expression. Lower bound is the value that I'm going to insert into the variable. And the upper bound, this is a point of confusion for some students. Upper bound doesn't necessarily mean that that's the number of terms you're going to see. It just means that the last variable that you're going to insert into the expression. So in this case, I mean, if we start at 1, then yes, our upper bound will always represent the same number of terms, the number of terms that we see. But here, we're starting at 2, so that 5 doesn't mean that there's 5 terms. It means it's the last I variable that you plug in. So there's only 4 terms here because we're starting at 2, we're going to 5. But a lot of times we do start at 1. So a lot of students assume that the top number always means that's the number of terms, but that's not always the case. Okay, so example 1, if I want to find the summation from 2 to 4 of I squared plus 1, then I'm inserting 2 in for I, getting that value, and then plus that summation just means I'm going to add up the next term. And I'm always going to increment by 1. So if I start at 2, then the next value is 3. And I keep going until I reach my upper bound. So here, there's only 3 terms because I'm only going to go from 2 to 4. Okay. Questions so far? Oh, the 2, 3, 4. The 2 came from the fact that our index is telling us to start at 2. So we plug 2 in. And then the next number, we're always going to increment by 1. So the next number is going to be 3. And then we just keep going until we reach the upper bound. So the 4 will be the last number that we plug in. Right. Any other questions? Now, these are summation formulas that we're going to use. Rather than adding all this up, we're going to have these formulas. So for instance, if I have the summation of I to 5, rather than saying, oh, that's 1 plus 2 plus 3 plus 4 plus 5, I have this formula that just says I can just take that upper bound and plug into this formula. This is the same thing as saying 5 times 6 divided by 2. Now, it's not a big deal if it's just a few numbers, but imagine going up to like 300, right? We don't want to add up all the numbers. It's easier to use this. I squared would just be 1 squared plus 2 squared plus 3 squared plus 4 squared all the way to my upper bound. Rather than adding up all those terms, I can go through this formula. Upper bound times n plus 1 times 2n plus 1 divided by 6. Same thing with summation I cubed. And then summation 1 is just 1 plus 1 plus 1, however many times. And number 5, this is going to be helpful for us to kind of help us separate our. So let's say I had this. Let's say I had summation of 4 over n I squared. It's nice to separate our constants from our variable. So we can write it this way, push that coefficient out, focus on what needs to be adjusted, and then that's where the formula goes. So I like to, this is a good property to help us see the parts that are not changing versus the parts that are changing, so we can kind of organize our formulas a little bit easier. Okay, so let me show you how we can separate this in an easier form. So let's say I have summation from 1 to 8 of 3i squared plus 1. I could plug in 1, then 2, then 3, all the way to 8. But I'm going to use my summation formulas here. I'm going to first separate into two sums. Sorry, I realized I did not give a lot of room here. So 3 summation I squared plus summation 2. Now this is I equals 1 to 8. I equals 1 to 8. Now, what I would like to do is I like to have the summation showing exactly the rule that I can see above. I can just make a clean substitution. So if I pull the 3 in front of the I squared, I can clearly see I have a substitution ready for me with summation I squared. But summation 2 looks a little bit different, so I'm going to adjust that. I'm going to say that's the same thing as 2 summation 1. And if I can write it out this way, then summation 1 I can just make the clean substitution that's equal to n. So with this one here, summation I squared, I'm going to write it out as n times n plus 1 times 2n plus 1 all over 6. No, I'll give these to you. Okay. So I'm just making a clean substitution from the rule in terms of n, and now I can replace every n with what? What's my n value? 8, yeah. So I'm going to skip that step here. This is going to get us to 628. I just want to kind of run through these examples here. Again, sorry for a limited amount of room. Now this one, it's best if we FOIL out first. So I have I squared plus 4i plus, just FOILing out I plus 2 times I plus 2. And every term will get its own summation. So I have summation I squared plus 4 summation I plus 4 summation 1. Okay. Summation I squared has its own rule. Summation I has its own rule. Summation 1 has its own rule. So we replace them in terms of n, and then replace all of them with 10. So it ends up giving us these numbers here. Okay, now example 4 is more like what I want us to work with, because when we push out our number of rectangles to infinity, we're going to have to leave things in terms of n. So treat n like your constant, and k is the moving part. K is what's changing, okay? So let's try this here. First, I can distribute that 1 over n through. I'm going to break them down into, let them each have their own summation notation. So this one is its own thing. I know I'm using k, but it's the same as I, just a different counter variable. Okay. So summation k squared can be replaced with n times n plus 1, 2n plus 1 all over 6. And then summation 1 can be replaced with n. Okay, that's as far as we need to do right now. I just want to be able to kind of get used to writing it out in that notation, and we're going to see how this is going to be useful as we talk about limits. We're going back to limits briefly because we're going to be letting the number of subintervals approach infinity. So there's that limit review that we have to do a little bit.
with this exact area.
Yes, that is what we're gonna work towards. Okay, I know I'm running out of time here. Let me do one example here, and then I'll pick this up tomorrow. If you're not gonna be here tomorrow, I'll have the video up so you guys can watch it. Okay. Now, let's say my function looks like this. Okay. What would be the limit as z approaches infinity? And remember, what's our strategy for approaching infinity? What do we do? We don't plug values in, right? What do we do?
Compare the powers.
Yeah, compare degrees, right? Compare powers. And really, the only thing you have to worry about is if degrees are the same, then it's the ratio of the coefficients. If the degree is higher than the denominator, it's going to go to what? 0. So that's the only situation you should see. You should never see a situation where the degree is higher than the numerator. If you do, we missed something. Okay. So let's do this. Limits as n approaches infinity of this expression that we see here. And what I want to highlight is the fact that we don't care about lower degrees. The highest degree is the one that we care for. So if we never worked out the cleanup of the lower value, it's okay. As long as we can clean up and identifying the highest degree and the coefficients associated with it, that's all we need, because the limit of this is simply what? Just 1/2. Okay, I'm gonna go right up to the bell if you don't mind. Let's go to example 6 here. Find the limit as n approaches infinity from 1 to n of 2i over n times 2 over n. The important thing here is that we only care to isolate the I, because that's what's changing. Everything else we're going to push out as a coefficient. So this is really the same thing as 4i over n squared. But I'm going to push that 4 over n squared out.
Why can you push out the 4 over n squared?
Because these are not changing. These are set in stone. It's the I that's changing. Because if we want to do limit as n approaches infinity, the limit, we have to convert everything in terms of n. So this is already set to ready to go. We just have to convert this in terms of n. So summation from 1 to n of I, if you look back on the previous page, is n times n plus 1 over 2. Compare degrees, my limit is simply what? 4 over 2, which is 2. Okay, so tomorrow, I know it's going to be a shortened class. I'm going to try to go through pages 10, 11, and 12. So I don't think I'll be able to get to first and second theorems of calculus until Monday. But at least I'm hoping I can finish this up tomorrow. Okay, come get your phones.
Take it during lunch.
Okay.
I have more time.
Yeah.
What is
If you are getting to the first and second, I think you're does that mean that it's the art instead of really? It's a lot. But I guess
That's right. Yeah. Yeah. I think on Monday I'm just going to be checking last Friday and today.
So what I mean, No.
Yeah, I think they're opposite.
I was.
Maybe easy black or tree.
You were here, I'm on.
Yeah.
And we think that's-